Problems on electromagnetic induction, chapter 29. And this actually represents what electromagnetic induction is. Because when you close the switch, the current in the primary circuit grows, and the growing current gives rise to an increasing magnetic field which is linked with the secondary, and so an EMF is induced in the galvanometer. Because according to electromagnetic induction, whenever a circuit experiences a changing magnetic field, an EMF is induced in it. That's called electromagnetic induction. Alright. And magnetic flux through a loop of area A, which is placed in a uniform field, is given by B times A, where you take the perpendicular component of the magnetic field. And so it's BA cos theta, or it could be written as integral B dot dA. So that is the formula for magnetic flux passing through an area. Remember that the angle theta is taken between the normal vector to the area and the magnetic field, as shown in the diagram. Now, Faraday's law, the induced EMF is equal to d phi by dt. The negative sign shows that the direction of the induced EMF is opposite to whatever is causing it. That is Lenz's law. And obviously for n loops, you got to multiply it with n. So when you combine both Faraday's and Lenz's laws together, that's when you get E is equal to negative d phi b by dt. So the faster the change in the magnetic flux, the greater the induced EMF. Now, this induced EMF can be produced in several ways. Number one, by changing a magnetic field directly by moving a magnet in or out. Number two, by changing the orientation of the loop. That means if you rotate a circular loop in a magnetic field, or actually changing the area of the loop by making it smaller or bigger. Okay, this picture represents how you could change the flux by decreasing the area by pulling on the loop. See, so these are the ways in which induced EMF can be produced. And if it's a moving conductor, and then by using Faraday's law, E is negative d phi b by dt, but flux is B dA, so when you differentiate, B is constant, taken out, and dA is actually the change in area, which is length times velocity times dt. And then that gives you E is equal to the product of the magnetic field strength, the length of the conductor, and the velocity. Now, in a generator, you have an axle, you have actually an armature that is rotating, and again by using Faraday's laws, you would get E is minus d phi b by dt, but the flux is, remember, B dot A, which is BA cos theta, and theta is omega times t, where omega is the angular speed at which you rotate the armature. Okay, so substituting all that, you get BA taken out because it's a constant. Differential of cos omega t is negative, and so two negatives make a positive. You get BA omega sin omega t. If there are n terms, you multiply with n. That gives you this equation, and you see that nBA omega are all constants, and it's called E naught, which is called the maximum value of the EMF or the peak value. Now that brings us to question number 1. In this case, you have a field that is first pointing up 0.68, then it's pointing down. So when you take the change, it's going to be taking down as negative 0.25 minus 0.68. And therefore the change in flux would be that multiplied by the area, which is pi r squared. So, and the unit of flux is Weber, remember that, because B is phi by A, right? So Weber, and then E is minus d phi B by dt, so divide by the time and you would get the answer as 0.053 volt. In the second question, you have the diameter of the loop changing, and you're asked to find the direction of the induced current. Remember, the induced EMF always opposes the cause that produces it. And in this case, the induced EMF must produce a flux into the paper. Why? Because the area is decreasing, so the flux is decreasing. It is this decreasing flux that's producing an induced EMF. And that induced EMF does not want the flux to decrease. Therefore, it sets up a magnetic field exactly in the same direction, which is into the paper. And the B part, to find the average induced EMF, d phi B by dt, take the change, it's B times dA by dt, because phi is B times A. Get it as 0.04288 volt. And for C, just divide it by the resistance to get the current. 0.017 amp. Alright, the third one, direct application. You're given the flux phi, and you have to differentiate that with respect to time, but there are 75 turns, so you have to multiply with 75 and differentiate that. Differential of t cube is 3t squared, and you get that. In the B part, just substitute t as 1 second and then t as 4 seconds in that equation. In this fourth question, remember that the antenna is actually cutting the horizontal component of the Earth's magnetic field, right? So since the Earth's field is given at an angle of 45 degrees, first you have to resolve it into vertical and horizontal, and then only take the horizontal component, because the antenna being vertical is cutting the horizontal. So that's B, BH, and okay. So you have we can find BH by B cos 45, and that is what has been done here. In the fifth question, it's a direct question because you're given the peak output, and the peak is NBA omega, rearranged to make omega the subject, and that you get in radians per second, but if you want it in rotations per second, you divide it by 2 pi. In the sixth one, the back EMF is given at a particular Okay, that's before we go to that, this is mutual inductance, which I will be teaching the next day, so I'm not going to explain that. Just remember that mutual inductance is when a changing magnetic field associated with one coil induces an EMF in a neighboring coil, and this is the principle of a transformer. And again, the LR circuit, the EMF's equation when you switch on is this, and you rearrange that, bring all the I terms together, integrate from 0 to I when t goes from 0 to t. So you get it off the form I is V naught by R 1 minus e raised to minus t L by R, which means the time constant is R by L for an LR circuit. And the current, the maximum current is of course V naught by R. Okay, so the time constant is R by L. That shows the decay of current given by a similar formula, except that the one factor is missing. So brings us to the sixth one. Back EMF is 85, and this is a comparison or a ratio problem, because you're given the back EMF when it's at 1100 RPM, and you're asked to find the back EMF, or you want to reduce the back EMF to 75 when the motor is running at 2300, and you're asked to say how would you do it. Well, of course it's by taking the ratio E by B omega. Know that the magnetic field has to be changed, because that's the only other factor that affects the back EMF. So you find the new magnetic field in terms of the old one. So if the new magnetic field is 42% of the old one, then you can achieve the back EMF to be 75 volt. Seventh one is about transformers, and if the voltage goes up, then it's a step-up transformer. Here the input voltage is given and the input current is given, but the output power is given. Alright, so it's a 75 watt transformer. From that you find that the primary voltage is 3.4, while the secondary was how much? 12. Therefore it's a step-up transformer. And what is the transformation ratio? That's Vs by Vp, which would be the same as Ns by Np. It's called the transformation ratio, which is 3.5. Well, the eighth one, the last one, it's always good to transmit power at a higher voltage and a lower current. From what's given, power is Vrms times Irms, so you can find Irms. The current is 1444 amps, and we know that the output voltage is the input E minus what is lost. Since we know the RMS is 1444 times 3, that's IR plus out. So you get the output voltage, and the loss is always I squared R, because that's the heat produced. And the percentage wasted is how much is lost divided by the total. And the total would be what reaches the town plus the loss. So 8.8% is lost. Hope you pay attention to all these problems and try to really understand how they have been done. Thank you.